Hello, everyone. My name is Ruairidh MacPhail, and I'm a master's candidate under Dr. Jean Hutchinson. Today, I'll be speaking about evidence of rock slope instability, specifically using videos to assess evidence. Throughout this presentation, I'll give a brief overview of rockfall and fragmentation. I'll then discuss the effects of fragmentation and predicting fragmentation. I'll go over the steps moving forward with this research and explain the specific benefits of video-based data. And finally, I'll go over the expected outcomes of this research. Rockfall is a diffuse natural hazard that threatens damage to infrastructure, loss of capacity, and in extreme cases, loss of life. Rockfall poses a particular challenge in Western Canada, where the mountainous terrain has led to highways, rail lines being constructed in areas exposed to the rockfall hazard. In order to protect against rockfalls, we must first understand how they occur and where they are likely to travel. Fragmentation plays a critical role in influencing the size, shape, and trajectory of a rockfall and all the fragments produced. Fragmentation produces less predictable rockfall outcomes. And that's because there is a possibility that fragments will follow significantly different trajectories than an intact block. At the point of fragmentation, the individual fragments can spread out, exposing a wider section of linear infrastructure to the hazard. At the same time, these fragments are smaller particles with less mass and destructive power than an equivalent large particle. However, specifically for railways, Abbott et al. In 1998 found that rocks with dimensions between 0.3 and 1 meter are a primary concern, as they are more apt to lift rolling equipment and cause derailment. It is for these reasons that fragmentation is a crucial aspect of rockfall hazard that is currently not well enough understood. So we'll move on to predicting fragmentation, and we'll do this together. The image on the right is a frame from a scaling video of this fragmental event. So how do we predict fragmentation? Well, let's go over it together. The image on the right is a frame from a video in which the section of the rock mass highlighted with a red circle is about to be failed by an airbag placed behind the rock mass. And I want to ask you, will the rock mass fragment? If so, when will the rock mass fragment? Will it disaggregate at initiation? Will it fragment violently on impact? Will it fragment in any other way? Why do you think that? How large will the fragments be, and how many fragments will there be? Now let's go over this video to truly understand how predicting fragmentation is not a simple task. As we saw in this video, the rockfall did fragment. However, only the areas on the top and the bottom actually fragmented, and this fragmentation occurred at initiation of the rockfall. There is a large chunk of rock that did not fragment, despite having structure. Giacomini et al. Explained fragmentation well in their 2009 paper by saying, fragmentation is probably the most complicated and poorly understood aspect of a rockfall, and very few useful contributions can be found in the literature. So I ask you, did you predict that result? Moving forward, there are two broad systems of fragmentation. A rock can either fragment along existing structure, or the intact rock can break. In a rockfall with existing structure, the fragments will often break along that structure. The number and size of fragments is dependent upon the impact angle relative to the structure for rocks with existing planes of weakness. The minimum fragment size and most fragment sizes can often be determined based on the structure pattern for fragmentation along existing structure. Intact rock fragmentation is less well understood. The lack of structure predefining possible fragments makes it more challenging to discern the potential fragment size and number. Fragment shapes are also not predefined by this structure, and so they vary significantly. Fragmentation research has been performed in a limited number of geologic settings, favoring sedimentary and/or foliated metamorphic rocks. And this has led to intact rock fragmentation being less well understood. Moving forward with this research, there is a need to update the understanding of fragmentation and its contributing factors and outcomes. Video-based data that captures fragmentation events are crucial as they permit real-time observation of fragmentation. These data, combined with the Rockfall database, give a 3D representation of the Rockfall object, as well as a video documenting how and why the rock fragmented in that way. Photos of the source area and debris pile are not sufficient to characterize a fragmentation event, as they lack information on the triggering factors and fragmentation process. This research takes many types of data, however relies heavily on photographic and video-based data. Survey information, photogrammetric models, and LiDAR information are all used as secondary sources of information. The LiDAR and survey information are used to give absolute scale to the photos and video information. The photogrammetric models can give either relative or absolute scale. When I'm talking about scale, I'm talking about the ability to discern the exact size and dimensions of an object in a picture. This enables quantitative analysis with videos. So how are videos useful? As I just said, videos can be analyzed in two different ways, either quantitatively or qualitatively. And this is very dependent upon the video quality and the design setup. The videos can capture the initiation and fragmentation of real rocks in real scenarios from various geologic settings. This includes any precursor rockfalls or secondary rockfalls. Videos have the ability to track where the fragmentation occurred. And this is something that's crucial to understand, whether the rockfall broke apart at initiation or at impact, and which impact and why. Videos allow the observation of fragmentation events in real time and show how the rockfall objects fragment and how the fragments behave. Here we'll go over a video analysis of rockfall initiation. There are 3 frames from the same video shown here. The frame on the left is the intact rock mass. In the middle frame, the rock block indicated by the number 1 has failed, as well as part of the area indicated by number 2. It's important to note that these 2 failures occurred prior to the failure of the rest of the rockfall. In the third image, we can see that the blocks 1 and 2 have completely failed out of the scene, and a tension crack outlining the back failure plane has now opened. Let's go over this in video format. The video shows that the block is not a fragment created during the fall of a larger rock mass and is instead a precursor rockfall. A second rock adjacent to the initial one falls slightly before the back crack opens up and the rock mass slides out. This video highlights the rockfall initiation process. Here we can see the video in whole. The rockfall shows 2 precursor events and the propagation of a tension crack. The rock mass then fragments along structure and disaggregates into smaller pieces during descent. Without the video, it would be impossible to tell the rock block indicated by number 1 from the rest of the fragments caused by the disaggregation of the rockfall. Videos enable real-time observation of fragmentation. Here we see 2 videos in which a rockfall object fragments. However, the fragments behave in a completely different way on the left and on the right. We've extracted 4 frames, 2 from each video seen in the previous slide, 1 frame pre-impact, and another post-fragmentation. Here we can see clearly that each video displays a different fragmental behavior. The images on the left show the fragmented rock continuing along the same trajectory. The images on the right, however, show that one fragment is bounced higher while the remaining fragments continue low. It's through this behavior that individual fragments can achieve greater bounce heights than the total intact mass. Scaling campaigns have great potential for video sources, and that's because the rockfalls are guaranteed to occur at the planned date. The traffic control allows for control over the camera setup location and view angle. The videos can be short and prioritize events that are likely to fragment through communication with the crew performing the scaling. It's also known where on the slope the rockfall will be initiated, and it's predicted where it will land. This allows the camera operator to capture the rockfall initiation, path, and final debris area in one frame without the need to pan the camera. This research can be integrated with previous research done by a number of colleagues within my group. This video-based analysis can be combined with current change detection and volume reconstruction research, resulting in a three-dimensional reconstruction of the intact rockfall object, as well as a video capturing the rockfall trajectory and fragmentation events. The rockfall object's shape, size, and rock mass structure can be mapped from LiDAR or photogrammetric models. The rock mass, lithology, and condition, as well as slope material, can be solved with the video or photo data and location data. Properly taken, high-quality videos can reliably solve for distance traveled, rotational, and translational velocities for the rockfall and all fragments produced. The three-dimensional reconstruction and lithological data can inform the physical characteristics of the rockfall, including mass, allowing for the computation of kinetic energy. The eventual outcomes of this research are to understand how various factors influence fragmentation. Several factors are predefined here as the block size and shape, rock mass lithology, structure and condition, impact energy and angle, and the slope material, with the goal of using knowledge over these various factors to better understand the fragmental rockfall hazard in terms of runout, lateral movement, fragment size, and shape. The key takeaways from this presentation are that fragmentation is not well understood. Fragmental rockfalls can be more hazardous than non-fragmental counterparts. Source area and debris pile photos are not enough to constrain fragmentation, as it lacks critical information about precursor and secondary rockfalls, as well as how the fragmentation occurred. Videos of fragmental events are needed to better understand the contributing factors. And these videos can be used in combination with current methods such as change detection and volume reconstruction to get a complete picture of a single fragmentation event. I would like to acknowledge all the members of the Railway Ground Hazard Research Group for their work to contribute towards this research, specifically CNCP and NSERC as funding members enabling me to continue this research. I would also like to acknowledge Mark Fish and the Washington Department of Transportation for providing the videos of scaling needed to put together this presentation, and Jean Hutchinson for her support and help throughout this project. Thank you very much for your attention. I look forward to your questions.